Welcome, dynamics students. This is the first lecture in a discussion of particle kinematics. So if you are coming to your study of dynamics from statics and probably having already taken some physics, dynamics basically can be divided, depending on how your course study goes, can be divided in four different parts, or have four different categories to what you're studying. First, are you looking at motion of something, the space-time relationship for something's position, velocity, acceleration, irrespective of what caused that motion? If so, you're in the realm of what's called kinematics. If you're more concerned with what got something moving or stopped it from moving, in other words, what caused its motion or lack thereof, you're in the realm of what's called kinetics. And that will involve a blend of both the motion and what caused it. The next category we can look at is, are we talking about a particle, either kinematics or kinetics, or are we talking about a whole body? And if you remember from your study of statics, a particle is something that is effectively so small that it can't support any moment. So we don't have to worry about equilibrium or moment rotational considerations for that very, very small body. And we also learned, or you have learned in your study of statics, that a particle, the definition of a particle was scale dependent. So a particle could be something as small as a portion of an atom or as large as a planet, provided that the frame and scale of reference around it was sufficiently large that whatever it was could effectively be considered to be effectively a single point, not to have any size, quote unquote. So we're going to start with kinematics, space-time, motion relationship, irrespective of what caused it, for particles, something that we can consider to have a single point. And just to glance ahead, one thing that we can do under certain circumstances that we'll define in this section of our study is we can take a body and treat it like a particle if we define that particle as the body's center of mass. Now, that is dependent on not having that body subjected to forces or other types of actions that are maybe area dependent, where the body would have to be considered as having size. But provided those conditions aren't in place, we can look at true particles that are particles via their scale, reference to everything else in the problem, or because they don't have any other loading where their size would matter, we can consider them to be particles at their center of mass. So, particle kinematics. We are going to look at space-time relationships for bodies that are sufficiently small that the locations of the material points, meaning the points around the body that make up the whole body, don't need to be distinguished. We can put them all at the center of mass, or just at a single point. Space-time relationships. So by space we mean position, and by bringing in time, we are looking at position at a given time. We're looking at the change of position with respect to time, otherwise known as velocity, at a given time, and the change in velocity with respect to time at a given time, otherwise known as acceleration. And all of these can be functions of time, and they can be any function of time. So next important set of maybe definitions and concepts are reference frames and vector derivatives. So these are kind of related. So up till now, you've probably studied calculus, so you're very used to taking derivatives of scalars, all kinds of derivatives. You've learned all kinds of rules for taking derivatives, and you can take a derivative with respect to time for a time-dependent function. You can take a derivative with respect to time for a non-time dependent function and, find that it's zero because it'll act like a constant. But what about taking the time derivative of a vector, something that has both magnitude and direction? Well, magnitude and direction, well, we can kind of separate those two. If the direction doesn't change with time, we can just end up taking the derivative with respect to time of the magnitude itself. But most of the time direction's changing, especially in kinematics where we're looking at motion. Something's moving. It's moving in a straight line. It's moving on a curved path. So if it's moving on a curved path, its direction is always changing as it moves down the path. So we definitely need to be considering our time derivatives with respect to how much is the magnitude changing per unit time and how much is the direction changing per unit time. And vectors provide us with a great way of separating those two effects. So just to give us a little visual of a vector whose direction is changing with time, and also to get us a little bit used to the idea of reference frames, we're going to look at this spinning disk, and it's spinning at 33 revolutions per minute. And this example came out of a fairly old textbook, and very likely the authors of that textbook were referencing a particular type of audio playback device known as a vinyl record that uses a piezoelectric needle that moves in the grooves that are inscribed in a plastic disc, and the movement of that piezoelectric needle produces a voltage signal that can then be fed to a speaker, and voila, you have music. So these are the old vinyl records. And 33 revolutions per minute was one of the standard angular velocities that it was played at. So we can look at this. This is kind of setting up for being a polar coordinate kind of thing. But if we imagine ourselves standing at point P and looking towards point Q, we're riding along on that spinning disk. And if it's big enough, we may not even notice that it's revolving. For instance, sit very still as you listen to this dynamics video. Could you feel yourself flying along through space at whatever velocity corresponds to the rotational velocity of the Earth? Changes with your latitude, probably. Probably didn't notice that. So that's akin to what's going on this spinning disk. We are sitting in the reference frame of something that we know is rotating around another point and spinning on its own axis if we were to look at a reference frame outside of the planet. So we think we're sitting still, and within our own reference frame we are, but from another reference frame we may not be. So the direction of a vector, say a vector r that connects point P and point Q, from the standpoint of something sitting on that disk, that vector doesn't change direction. It's always pointing from P to Q, because P and Q can't tell that they're moving on their own disk. If you're out here at O, relative to some, reference frame outside of the spinning disk, these things are changing direction all the time, very quickly, in fact. So if you're sitting at point O and you're looking at vector r and someone says, is vector r changing length? You go, no, but it's sure changing direction. But if you were standing at point P and asked the same question, you go, no, it's invariant in both length and direction with respect to time. It's always pointing the same way, just like north always points in the same direction from your own reference frame somewhere on the Earth, depending on, again, on where you are, declination aside. So this is an example of how you can have, first, a different change versus time in magnitude versus direction of a vector, and second, how either one of those, in this case just direction, changes with the reference frame that we're on. So from the reference frame of the spinning disk, neither magnitude nor direction is changing, but from the reference frame, any reference frame external to that spinning disk, magnitude may not be changing, but direction's definitely changing. Okay. So having established that, it's really important to be able to take time derivatives of positional or space-related vectors, in fact, any vector, but definitely ones related to position, velocity, and acceleration, since that's what we use to describe motion. So we're going to take a little vector calculus now. We've done some vector algebra, and because we're taking derivatives, we can call it calculus. So we're going to look at general ways that we can take a time derivative, or really any derivative of some vectors using properties we know of vectors, especially multiplication. So let's start with a vector multiplied by a scalar. So we got vector A somewhere pointing around in space, and we want to multiply it by a scalar. We want to cut its magnitude in half or double it or something. So in this case, alpha is some scalar, and A is a vector. So if we take the time derivative of a scalar times a vector, we can just apply the rules of multiplication of a product and say, great, that equals to the derivative of alpha with respect to time times the whole vector A plus alpha, just the scalar, times the time derivative of the vector A. So this is just literally VDU plus UDV, definition of a derivative of any kind of product. And we can also look at the time derivative of a vector sum. So the derivative of a sum is the sum of the derivatives, just like we've seen for integration with things like centroids and center of masses. So we can apply that to vector quantities too. And thinking about it, each one of these vectors is itself the sum of its component parts across all three orthogonal directions. So we're going to use this particular rule of the derivative of the sum being the sum of the derivatives applied to vectors when we want to look at the time derivatives of vector components in all of its component directions. We can just go ahead and take each one of those separately, because vector components expressed in terms of three orthogonal directions, I hat, j hat, k hat, r hat, theta hat, z hat, whatever, those are just a sum. So we'll use this quite a bit. Okay, how about multiplication? Well, with vectors, two types, two flavors. We have our dot product, where we're going to end up with the portion parallel to each other of vectors A and B in this case. If we take the time derivative of that, we have something that looks real similar to what we have above. Vector product, we're going to do the derivative of a product. So in this case, the product is the dot product. So we just have derivative of vector A with respect to time, dot B, which, oh, by the way, now we're almost exactly like we were up there, because in this case, we've got now a vector quantity dotted into another vector. We're going to end up with a scalar. So here we've got a vector now. We got A, vector A, dotted into the time derivative of vector B, which will give us two vectors. We'll dot them into one another, and so this whole expression will end up being a scalar, which is what we would get if we worked out the scalar product first, which of course we're not going to do. It's not correct, but we end up with a scalar as our derivative expression. And likewise, if we look at the cross product, we can do the same kind of thing. A time derivative of the first term multiplied, this time cross product multiplied by the second, plus the first cross product multiplied by the time derivative of the second. So all vector variations on the definition of the derivative of a product. In this case, it's the time derivative. So these are all our handy tools that we'll use anytime we need to take the time derivative of some vector expression, which might tell us where something is, how fast it's going, or how it's accelerating. Okay. Other important things about vector expressions. Remember, just as a super basic review of vectors, but we can express any vector in terms of three mutually perpendicular unit vectors. And in this case, we're denoting them real generally with e's and a subscript. So e sub 1 with a little caret, meaning unit vector direction e1, and same with 2 and 3. These are all perpendicular to each other. Now, because a lot of times we're going to have things traveling on curvy paths, those E1, E2, E3s, they're not always going to be I hat, J hat, K hat, which are the mutually orthogonal unit vector directions for Cartesian coordinates, which are straight lines all perpendicular. We may end up using ones that move around in circles. So our E1 hat may be a radial direction, our E2 may be a circumferential direction, like a theta direction. And our E3 may be another theta direction, or it may be a height. So we can use cylindrical, or we can simply define things in terms of our path. Are we going along the path? So E1 may be tangent to the path, and E2 is normal to the path. So tangent and normal are two other vector directions that we might have, in which case we might have a couple of orthogonal normals. So all kinds of different unit vectors that we might use to conveniently describe motion depending on what kind of motion we have. And of course we have certain magnitudes of our overall total vector in each one of those. So we could have so much going in the I hat, j hat, k hat. We could have so much magnitude in the r hat, theta hat, z hat, etc. So much in the tangent normal. It's we're going to use all of them depending on what the motion looks like. What is going to be common to all of them is there's going to be a reference frame that defines the motion. And you can think of it as point of view. The motion or the position is 3 feet over, 2 feet to the left, or it's 3 feet over and 45 degrees counterclockwise with respect to what? So reference frames, reference positions, points of view. If you find yourself asking so far, so fast, with respect to what, means you need to get the reference frame straight. You need to have that point O or P or whatever is your reference system defined, because that literally defines everything about all of your motion vectors. So the idea of a so far, so fast, with respect to what, is a fundamental kinematics thought. And that thought of with respect to what is known as the reference frame. So we use, in this case, a scripty letter. So in this case, we have kind of a cursive F, meaning reference frame F. So if we're gonna define the time derivative of our vector A in reference frame F, we put a little F as a kind of a forward superscript right next to our expression for the vector or one of its time derivatives. And if we're going to write out this expression, including its component unit vectors, using our definitions of derivatives of a product, we would multiply everything out. So this is A. A is the sum of 3 products. So to take the time derivative of A in its reference frame, we're going to take the time derivative of the sum of 3 products. So we'll have time derivative of the magnitude of A in unit vector direction 1 times the unit vector in direction 1 plus the magnitude of vector A in the direction of unit vector 1 times the time-dependent change of that unit vector. Maybe the whole system's spinning like that disk. So obviously we've defined a reference frame that doesn't contain those unit vectors, otherwise this expression would be 0. And we can go on for the other components. So again, time derivative of a magnitude times its unit direction plus that same magnitude times the time derivative of the unit vector itself. So this is a direction change, this is a magnitude change. And depending on the reference frame we've defined, these unit vector directions might be fixed and these terms go away, or they might be changing and we have to figure out how they're changing and then include them in our kinematics expressions, our equations of motion. So we're going to start with a little example. We're going to go back to our spinning disk and we're going to say it's spinning at 33.1/3 RPM. And we're going to define a vector A here that connects point P to point Q. I'm going to get ready to scribble a little bit. And this is the center point of the spinning disk. The disk is out here in big circle. And so we're spinning about that point. Well, the disk is spinning about that point. We may or may not be spinning with it depending on whether we're sitting on it. But this is the center point. So we could define our vector A, which connects point P and point Q, as in terms of the center point. But we've been asked to find an expression for the time-dependent change of this vector A here with respect to point O in some reference frame F. That I'm going to try to draw, which is not spinning. So now we've got to look at vector A, which has an ever-changing position. Drat. It's pretty easy to express the direction of P to Q with respect to the disk that's itself spinning. It's always going basically in the same direction because our reference direction is always changing. It's always 3 inches, I guess, up, because up is always the same. But we want it with respect to point O, where effectively this direction is always changing. So we need something that connects the reference frames. How do we express the time-dependent change in the disk reference frame to the non-spinning reference frame? So we need to connect the two reference frames in order to write that time-dependent change in vector A. And so to do that, we're going to find a function theta of t, which is our connector function. And so some of these lines are a little faint. So I'm going to draw these in a little bit more. So if we start with our I hat, j hat directions with respect to our point O reference frame, the one that's not spinning. If we're in this reference frame, in the point O reference frame or big script F reference frame, that is not spinning. That is not spinning. The X and Y directions aren't changing with time. A is changing with time, X and Y are not changing with time. So the time dependent derivative of in this case I hat and j hat is going to be 0. Okay. So I'm going to draw vector A kind of as a function of our theta angle, which is changing with respect to time, because I actually know the rate at which this angle between the center point and the I hat direction here is changing. I can define the I hat direction up there. That's a direction. It's changing at 33 1/3 revolutions per minute. So it's a constant function with respect to time. So I know what it is. So now I just need to look at how would I express this vector A in terms of this connector function to get it in terms of X and Y. Well, I just use some geometry in this case. I can project a position up here of theta that connects me to Y and X. So I've got that written down over here. So I can write my vector A, instead of being just 3 inches up or whatever from P to Q, I can write it in terms of I hat and j hat out here in the F fixed reference frame, I guess, as opposed to the spinning one. So to get my position from wherever P is to wherever Q is, I'm going to move effectively this far in the I hat direction, and I'm going to move that far in the j hat direction to get from any P here to any Q up here. Q's up here where I have the arrowhead. Okay, so I go up and over. And that's how I write that with respect to my x, my fixed reference frame. Okay, I need to express this over and up for the I hat j hat in terms of my connector function theta. So what is that? Well, I use some trig because theta is this angle in here. I go back to just my pointer. So I can say, well, in this quadrant at least, I will move -3 inches sine theta, which is changing with time, in the I hat direction, and then I'll move up 3 inches cosine theta in the j hat direction. I hat and j hat are tied to my fixed reference frame. So I've used the dimensions of my spinning reference frame, and I've used theta as a function of t, which connects the spinning reference frame to the fixed reference frame to write an expression for vector A in terms of the fixed reference frame, or fixed with respect to point O. Okay, now I can take my 33, and it should have been a third, revolutions per minute, and I can express it in radians, so 2 pi radians per revolution, 60 seconds per minute, times t. So that's at any time I will have gone, this many radians. So I end up with 3.49 times t radians, where t is in seconds. So the 3.49 would be in radians per second. So the more seconds, the more radians. So this is a linear function. So I'm going to take the sine or cosine of something that's going to change with time. So if I insert that in, I can insert that in as a function, time-dependent function of theta up in this expression, and take as many derivatives as I need. So before I pop that in, I'll just go ahead and take the time derivative of this expression here, and I can always insert my linear expression for theta of t if I need to, when I need to. Okay, so I'm going to take look, I've got the sum of two expressions, each of which is a product. So I'll apply my derivatives with respect to t of a vector expression. So I'll get the derivative of my sine term and my constant, all my scalar terms. So I've got the derivative there, 3 inches. Derivative of sine is cosine. Times the derivative of the what the sine is operating on, so that's d theta dt, which is great because I have an expression for theta, times I hat. Now, if I hat itself were changing with time in the 0.0 reference frame, I would have an expression that says -3 inch sine theta times d I hat dt. But I hat and j hat are not changing with time in the 0.0 reference frame. So there's no time-dependent change in I hat. That's 0. So we knock out, effectively, this term is 0 in the 0.0 reference frame. Very handy. So we ended up just having the derivative of our reference frame coupling term, theta. It's coupling the spinning and the non-spinning frame. So we do the same thing with our j hat term. And then we can pop in our expression for theta with respect to time and put in whatever time we need there. So we have cosine of, basically cosine of about 3.5 t, and then our d theta dt was just a 3.4, which ends up in front. So just sort of doing some substitution. So at any given time, we can just simplify this, and if we said theta equals 3.49 t, we now have an expression for how fast our vector A is changing with respect to time from the point of view of our 0.0 reference frame. And if we wanted to know, and this is, of course, our expression for velocity. We could take another time derivative if we needed acceleration, which is a point. For our next lecture, we'll continue with that. So the sine and cosine functions connect the PQ reference frame on the spinning disk, which A vector is always pointing straight up 3 inches in the spinning disk, to always going in a different direction according to this trig function in the point O reference frame. So this is our kind of like our coordinate transform expression for the velocity. By the way, the velocity, the time-dependent change of our vector A within the spinning disk, nothing changing, be 0. So our only main change in this case, really, what we're looking at here is the change of the reference frames relative to one another. So that's all you're really seeing in this case. You could have had something that's moving on the spinning disk itself. So one of the classic examples of two things moving, the reference frames moving between them, is the infamous spider on a frisbee relative reference frame expression, which you would solve just this way. So in that case, point Q would be moving with respect to point P within the spinning reference frame. And that's no big deal. We would just simply have a time-dependent expression for A, which we would then connect with theta. But start with something simple. So that is the end of this lecture. So we've made a little introduction to dynamics. Are you only interested in equations of motion? If so, kinematics. If you cared about what got the motion started or stopped, you're in the realm of kinetics. So we started with kinematics, and because we were working with bodies that are small enough that they don't have any size, or there's the scale with which we're looking means that they can be considered points, or we can just look at the center of mass of a body, no moment being supported, we got particles, or body center of mass is acting as a particle. So that was definitely the point in this case. We were looking at point Q as a particle and a vector pointing towards it. So particle kinematics for this lecture, and we will continue in the next lecture looking at the time-dependent relationships between position, velocity, and acceleration a bit formally. We'll review of physics, which will continue through the rest of the course. Important concepts.